Try to be a bit attentive, okay, for this one, how the calculation is done. All right, so in order to calculate, I have only written the delay subroutine. I have not written the entire code because we are only interested in finding the delay using the delay subroutine. So I have not written the entire code. So for finding this exact delay, you need two things. First of all, what is the crystal connected and what are the machine cycles for each instruction. These are the two things that you need to know. So say the information provided to you is that the frequency of the connected crystal is 11.0592 megahertz. So based on this crystal, definitely you have solved you have found the time period. So can anyone tell me what is the time period for this crystal?
So 1.085 microsecond.
Exactly, 1.085 microsecond. Now, most of you already know how many machine cycle is needed for all this instruction. Like for moving, how many machine cycles do we need?
Sir, 1.
Exactly. So for all the move, we have got one machine cycle. For DJNZ, how many machine cycle?
So 2.
Exactly. So 2, and for return we need another 2. So this information will be provided to you by some way or other. So you have this information. So now you can calculate what is the exact delay. So how do you calculate the exact delay in seconds? So let's see. In order to calculate this delay, you will always start from the innermost loop or from the loop which is encountered most. If you look at this delay subroutine, you will see that this L1 will be encountered the most, or it will be, this is the most inner loop among all the loops. So the machine cycle is 2. So initially for this loop only, how many times will this loop run?
100 times.
How many?
10 into 100 into
For
100.
one cycle of L2, it will run 100 times.
For one cycle, exactly. I'm asking just for this line. So in this line, it will only run for 100 times. So you can simply write 2 into 100. Okay. When you do this, you give a tick to the machine cycle which you have incorporated. So we have incorporated this machine cycle. All right. After this, we will go to the next line. In next line, we see that DJ NZ R6 L2. So from here, you will come in this line. That means this particular line, this is controlling this level. Okay. If it is controlling this level, that means this line is associated with these 2 machine cycle and 1 machine cycle. So you just, after this calculation, you simply add 1 plus 2. I mean the extra machine cycles are coming. You have already incorporated this machine cycle. So no need to incorporate it again. It will automatically be incorporated. So what are the extra machine cycles? These 2 and this 1. So how many times will this loop run?
100 into 100.
Why 100 into 100? I'm talking only about this loop. It will depend on the value of R6. So what is the value of R6? Exactly, only 100 times. So you just multiply it by 100. Okay. So we are done incorporating all these 3. After that, you will come in this line. So you see that now this line controls the level over here. That is L3. So just write the extra machine cycles that you have not yet incorporated. So what are those? These 2 and this 1. So put a bracket. I'm not following the order of the bracket. Okay, it becomes difficult. I need a lot of brackets. So plus 2 plus 1. Now, how many times will this loop run?
10 times.
Exactly, 10 times. So now you multiply this entire thing 10 times. Oh, sorry. Multiply this with 10 times. You see that we are not taking this inner loop because they are automatically being multiplied once again. Okay. So that's why we do not need to incorporate it time and again. After this, we still have 2 machine cycles that we did not take. So after this calculation, just add 1 plus 2. So you have taken this one and this one. So you see these 2 machine cycle or these 2 instructions will be executed only once. So now you have incorporated all the values of the machine cycle. After that, what you do? I mean, this one is continuing, okay? Plus 1 plus 2. Okay, let me write it over here. It will be easier for you to understand. So I get after this 10, sorry. I need another bracket. So with this adding 2 plus 1, you get an extra 3. So this will give you your total machine cycle. You will get your total machine cycle. So your delay will be simply equal to, delay will be your total machine cycle multiplied by 1.085 microsecond. Whatever you get will be your answer. Is it okay? Did you understand the calculation? Any question? Come on, anyone.
Sir, can you repeat one more time?
Can I repeat one more time? You need to specify which portion do you want me to repeat.
First part.
Huh? Which portion?
First part.
First part. First part, last part. What are you saying? I can't hear. Say again.
I mean, like, maybe that you could play it from L1.
So you start me to begin from, to start from the beginning.
Yeah, just the first part. I understand then the last part. Only the first part.
Okay, this is the okay. I'm explaining from the first again. But remember, if you do not understand any portion, you need to stop me right there. If you say that, sir, start explaining from the very beginning, it becomes very difficult for me.
I understand the last part. Only I need to understand the first 2 parts.
Okay, so you start with the innermost loop. You see, this is your innermost loop. So initially, this loop will run how many times? It will run 100 times. That's why we have written 2 into 100 over here. After finishing this line, we go to the next line, DJNZ R6 L2. You see that this line will take you to this level, L2. That is what I have shown with this bracket. So except these 2, what are the 2 extra machine cycles? This one and this 2. That is this one and this 2. So you simply write 1 plus 2. So how many times will this loop run now? The one that I'm marking this green. So this one will run based on the value of R6. What is the value of R6? The value of R6 is 100. So that's why you multiply this Sorry, this is second bracket. Yeah. So you multiply this entire thing with 100. Then you extend this same logic. What are the next two extra machine cycles? This machine cycle and this machine cycle, because this line controls the label over here. So we simply write extra 2 plus 1. Now, how many times will this loop run? It will depend on the value of R7. What is the value of R7? 10. That's why now multiply this entire thing with 10. Then you will see that we only skip these two machine cycles. So 2 plus 1 will give you 3. Whatever you get, that is your total machine cycle. So you multiply your total machine cycle with the time, that is 1.085 microsecond. Whatever you get, that will be your answer. Is it okay now?
Yes, sir.
All right. Any other question, anyone? Okay, so please be careful while making these calculations. Say.
So what if we want to implement certain time of delay? So how to approach that?
Okay. That's a good question. So what if we want to implement a certain type of delay? So if you want to go for implementing, I mean, if your question is write a delay subroutine for for generating a delay of 25 millisecond, 25 microsecond or something like that, in that case, you actually cannot execute this calculation. This becomes very difficult. So this one is known as the detailed calculation or more exact calculation, but there is a short version also, which is known as a short calculation. What you do is, you will simply focus on the inner loop. Okay. So I'm showing you the short calculation over here. So we will simply focus on the inner loop. We'll neglect any other instructions. We will just focus on the inner loop only. So how many machine cycles we need? 2 machine cycles. So just write 2 machine cycles. How many times maximum can you execute this? Okay, let me show this for this example. Then you will automatically understand. So 2 machine cycle, how many times will it run? It will run for, we have got 3 levels. So that means it will run for 100 into 100 into 10. Now you multiply with 1.085 microsecond. Whatever you get is the answer. This is known as a short calculation. What we are doing, we are neglecting rest of the machine cycles. We are simply using the innermost loop, which is executed for the most number of times. So we just write how many machine cycles we need. How many times will be repeated? It will totally depend on the number of levels. So we have got 3 levels. Who are controlling these 3 levels? R5, R6, and R7. So simply multiply R5, R6, and R7. Then you multiply your time period. Whatever you get is your answer. This is known as a short calculation, and you will use this short calculation when you want to design a specific time delay. So how can you do that? So you already know what is the machine cycle. I mean, it will be DJ and Z. So you will write 2 machine cycle. The maximum number of time that you can multiply at a time is 255. Then you have your option of X into Y. It should be, okay, sorry. Then it will be multiplied by your time period, say 0.85, whatever is the time period. This should be equal to the exact time delay that you want to generate. Say you need to generate 25 microsecond. So now you need to find the value of X and Y. So based on you can choose any value of X and Y as long as this calculation gives you an result which is approximately equal to 25 microsecond. If you need more values over here, so you can use X into Y into Z. I mean, you can use more levels. This is simply the number of levels. This one I'm showing you for 3 levels. So if you use more levels, you can keep on multiplying this thing as long as your result does not become equal to the exact delay that you are trying to generate. Did you understand?
Yes, sir. But it will not give exactly 25.
It will never be exactly equal. You see? Now try to think in this way. We use microcontroller for what type of devices? For devices like fridge, television, oven, all these things. And you are already dealing with microsecond. So even if there is a deviation of say 20 to 30 microsecond, is it ever possible for anyone to identify?
No, sir.
So it doesn't matter. The only way you can get the exact time delay is using an oscilloscope. Even you cannot measure the exact time delay with any other thing. And in the applications that require your music, it does not bother about a slight time delay. That's why you will see that in your book, all the calculations of time delay is approximate. It will never tell you that this is the exact time delay. all these delays are approximate. So as long as your approach is correct, you will get your marks. It doesn't depend on the answer. Clear now?
Sir, what does 2 MUC mean in the first term?
To MC, machine cycle. You need to know how many machine cycles we need. That is the machine cycle.
So that is the inner loop. That indicates the inner loop, sir.
Yeah, that indicates the inner loop because you will always use DJNZ. So you need to know how many machine cycle is required for DJNZ instruction. So it will always be 2. But again, I'm repeating, if the question is generate a time delay, then only you will use this formula. But if a code is given, if a delay is given to you and you have been asked that calculate the delay generated by a given code, then you need to follow this approach, which is more accurate. You need to know both the things, okay? Let me start today's class now. It has already been more than 20 minutes. Today's class is actually very short, don't worry, it will be very small. We will start a chapter and we will finish that chapter, okay? Chapter 4. Most of the things of chapter 4, all of you already know. All right, so we have got a total of 4 ports in our MUSI, and all these ports are used for input or output operations. We have got a total of 30 pins which are divided into 4 ports. The name of the ports are P0, P1, P2, and P3. So we have a total of 32 pins, means that in each port there will be 8 pins. That's why it is known as 8-bit ports. The individual pin, they act like a single bit. So that's why it is known as a 8-bit port. Now the last point is important. You can use the pins or ports either to work as input or as output. So how do you specify that? If you want your pin to act as input, you initially set a value of binary 1 to that pin. And if you want your pin to act as output, you set the binary value 0 to that pin. So let us see an example, then it will be much more clear. But as for now, the few things that you need to know is that we have got total 4 ports. In the 4 ports, we have got 32 pins which are equally divided into those ports. That's why each port becomes 8-bit ports, and the name of the ports are P0, P1, P2, and P3. Now let us see how it acts as input and output. So we have got two examples. In one example, the ports act as output. Look at the title. It says ports as output, and I have given the example for port 0 only. But instead of port 0, you can use any port you want. It is equally applicable for all the ports. And on the right hand side, you can see the example where the ports act as input. So what was our first condition of making the port act as output? We need to send the value 0. If you send a value 0 to the ports, your MUSE understands that this port will act as output, meaning that it will control any device or any peripheral equipment that is connected to the MUSE. Then we have got a normal code. I mean, in this code, it will toggle all the bits of port 0. We have already seen this example in our previous classes, so nothing to explain over here. On the right hand side, we need to configure the port as input. So how can we configure the port as input? We need to send binary 1 to the ports. So you see in this line, we send binary 1 to the ports. Now your MUSE understands that this port will act as input, meaning that whatever device is connected to that port, your MUSE will receive data from that particular port. Now look at the code. So what you are writing, move A, P0. So whatever device is connected to that port will give you the data that you are storing in the register A. After that, what you do with that instruction is totally up to you or up to the designer. In this particular example, whatever data you receive from port 0, you are sending it back to port 1, and then we again jump back. Okay, so now if you have any question in these two examples, you can ask.
Excuse me, sir. Sir, I got disconnected. Can you explain one more time?
Okay. Did you see the output portion, or I will start from the output?
Sir, from the output portion.
All right. So what was the condition of making a port act as output? The condition is we need to send binary 0 to that particular port. So in this line, we are sending 0 to that particular port. So your MUSE will understand that this port will act as output. Then we see the following code. I mean, this was already there in your previous examples. This code does nothing. It simply toggles all the bits of that particular port. So whatever device is connected with that port, it will behave accordingly. This is how your port acts as output. Now, if you want your port to act as input, then we need to send binary 1 to that port. So in this line, we are sending binary 1 to that port. So your MUSE will understand that I will take data from any device that is connected with this port, because this port will act as input now. So you see in this level, when we start, we write move A, P0. So whatever is there in P0 or in port 0, all those data will be transferred to register A. Try to see that your port 0 is an 8-bit port. So definitely it will send you a 8-bit data or 1 byte size data. And your register A is also a byte size or 8-bit size. So you will, I mean, the size is exactly the same, so there will be no problem with that. Then after getting the information from the port, what you do is totally dependent on the designer or your problem at hand. In this particular example, what we are doing is we are reading the data from port 0 and we are sending the exact same data to port 1. And then we jump back and we keep doing this indefinitely. Is it understood now?
Yes, sir.
Look at these things. In the second example, we moved this value via register A, but in the first example, we directly move the value. So you can do any of, I mean, you can use any of this instruction. Either you can use via a register or you can directly use. That is totally up to you. Also over here, we have used a via instruction. That is, we have used register A, but you could have simply written move P1, P0. This is also a valid syntax. You can directly move from port to port. No problem with that. So is it clear up to this? Any question?
Can we move 0FFH directly to port 0?
Yeah, you can move. That is what I just said. Instead of these two lines, you could have simply written move P0, hashtag 0FFH. That is also correct. That is what we have done exactly over here. So if you can move 008, definitely you can move 0FFH as well. Doesn't matter. Is it okay?
Yes, sir.
Moving on. This is also very simple and straightforward. Whenever you reset your MUSI or you start your MUSI, initially all the ports have this corresponding value. That is, all of them contain binary 1. So what does that mean? Whenever you start your MUSI or whenever you reset your MUSI, your ports are configured as input by default. So if you configure it as output, you need to send an extra 0 to those ports. In only then it will act as output. Otherwise, by default, they will act as input. Try to recall the code that we had in our lab. We sent an extra 0, and in the comment section it was written as upon reset all the pins work as input. So this is the explanation or why it happens. This is the system how it has been designed. Any question over here? I don't think so. This is very simple.
I have a question, sir.
Go.
Sir, can we set some pins of a port to be an input pins and some to
Got
be
your
output?
question. I got your question. That is our next topic. And in short, to answer your question, the answer is yes, you can. How to do? Look at this now. this is your section 4.2, that is input output ports and bit addressability. So instead of accessing the entire port at once, you can access the individual bits or individual pins of a port without affecting rest of the pins. And this is considered as one of the most powerful features of your MUSI 8051. Okay, so what I just said, that instead of accessing or using the entire port, you can also access single bits or single pins within a port. How we can do that? The instruction is, I mean, whatever instruction you write, of course, it will be bit instruction. It has to be bit instruction because you are accessing a single bit. So the instructions has to be bitwise. And this is the main syntax, that is x dot y, where x is your port number and y is your pin number. Look at the first example. So within the back label, what we are writing, complement P1.2, that means complement pin 2 of port 1, call delay short jump back, that is keep on doing this indefinitely. Let's look at the second example. Now what we are writing, set bit P1.2, that means set the second pin, not second, actually set the pin number 2 of port 1 as 1, call delay, now clear the pin, that means set pin number 2 of port 1 as 0, again call delay and short jump back. One small thing you should always remember, when I give you a register, you know that which one is the MSB, which one is the LSB, and we said that you can transfer the entire thing to a port as well. So you need to know that which pin within a port will act as input and will act as MSB and which will store the LSB. So any port you have, in any port, your pin number 0 will always act as LSB, and in any port, your pin number 7 will act as MSB. So you need to know this information. Okay, fine. Is there any question up to this?
Sir, in the second code, short jump, it will be again, I think.
Yeah, right. It will be short jump again. Thank you for that. Do not do that, right? Yeah, it will be again. Thank you. Anyone with any question? Okay, so you see that I can often make this type of mistakes, and this is definitely not intentional, right? So I mean, when we start teaching, we sometimes we don't have the exact sense of what we are writing and not what we should write. So when you go through the recording or when you see the video, if you find something that you think might contain some mistake, and if you are confused, I mean, if you are not confused, you can correct it by yourself. But if you find something that is confusing, definitely you can let me know that, sir, on that day, on this time, you said this or you have written this, but is it correct or should not it be like this? So you can reassure it from me. You can get the assurance from me. Okay. So let us move on. Let us see an example. Actually, in this chapter, in chapter 4, there are a lot of examples, and most of the examples are very same. So I will just show you one example, and I'll write the question for this example because let me explain it. The rest of the examples, please see it on your own. These are very simple, very easy. I mean, at least compared to chapter 3, what we had in chapter 3, compared to that, chapter 4 is very easy. Okay, let me write the question first. question we have in this example 4.3 is, you don't need to write, okay? I mean, this is there already in your book, I guess, in the soft copy also. So you can just see from there, just look at the explanation. So keep monitoring pin 0.1 until it becomes high, okay? So that means you understand from this portion that you need to make this pin as an input. How can you do that? You can use this line over here. Say in this line, what you are doing, you are configuring pin 0.1 as input by setting bit 1, that is by sending a binary 1. So we are setting this, we are configuring this pin to work as input because we need to keep monitoring this pin until it becomes high. That means until it gets logic 1 or it becomes high. It's the same thing. Then when P0.1 or pin 0.1 becomes high, read in data from port 1. That means what? Port 1 should also act as input. So in this line, we configure port 1 as input by sending binary 1. All right, so we are done up to this. This one gives you the solution of part A. That is, keep monitoring pin 0.1 until it becomes high. So what is the meaning? JNB is, the meaning of JNB is jump if no bit. So what your JNB will do, jump if no bit, then you will give the bit address. So this instruction will constantly check the value of the bit over here, that is P0.1. As long as the bit is low or as long as it contains binary 0, this condition will be true because the condition is jump if no bit. So if there is no bit, that means it will contain either 0 or it will contain low value or low voltage, like 0 voltage, same thing as binary 0. That means this condition will be true and it will keep on jumping in this level. So when will this condition be violated? This condition will only be violated if there is a bit. That means if it becomes high. So what we will do, if it becomes high, we will read in the data from port 1. So this one gives you the solution of part B. See, we are reading the data from port 1. That is, we are sending the data to register A. After that, what do we do with the data? That is totally a different thing. Okay, once we have read the data, what we need to do? We need to send a low to high pulse on this pin. That means we will send a low pulse first or low value, that is binary 0, and then we will send a high value. So these two will combinedly give you the solution of part C. Was it difficult to understand? Is it understood after this? Yeah, say.
Sir, in the beginning of the code, we have already set the value of P01. When we set it as P01, the value is already set as 1, right, sir? Because it's set bit. So in the instruction again, so why are we at all jumping at this point? Because its value is already 1, sir. So why is this jumping procedure initiated? The bit is already 1.
I got your confusion. You see that when initially you are setting the value over here, like set bit P0.1 as input, initially when you are setting this value as 1, what your MUSI does, your MUSI will go to that, I mean, it will see that particular pin and definitely some device will be connected with that pin. So initially when your MUSI sees that you are setting the value in that bit as 1, your MUSI will understand that I will control that device. Sorry, I will not control, sorry, I will read data from that device because I am configured as input, or that pin has been configured as input. So the target will be to read data from that device. This value, that is set bit value, this will not be moved or this will not be checked with JNB instruction. This is a difference between a value and latch, and I don't want to go to the latch portion. Okay, that is not included in the content right now. So just know that the initial value that you set only tells the microcontroller whether it will act as input or as output. Then when you go for checking the bits, this value that you have set initially over here, this one does not affect. It totally depends on what you are getting from the device. Did you understand the difference? I got your question actually. Yes, did you understand the difference?
Yes, sir.
Good question. So this thing is actually known as port latch, and normally this thing is not covered or included. So no need to get worried about that. Your MUSE can automatically distinguish it. Okay. Any other question? If you do not,
Sir, sir, we need to have the pin bit as 1 to get it,
input, right?
but when the pin is getting input from outside as 0, then
no, it will not change. That is, these are the different things I told you. When you set it at the big, so you set it normally at the beginning of the code. When you set it for the beginning of the code, your MUSE understands that you are setting it so that it can work as input or output. Once it has been configured as input, whatever you get from the device, it does not affect the configuration of the port. To configure that, you need to reset it once again.
okay, sir.
All right.
Sir, sir, in the second line, sir, they have moved P1, comma 0FFH.
Exactly, yeah.
So if I write here move P1, comma 00H,
Then port 1 will act as output.
yes, sir, then it will act as output. But in line number 4, when we read data from P1, if I want to read 00, then what can I do? Then I have to set P1.
I got your question. I got your question. But once you set your pin or port as output, then instructions like this, they become invalid. It does not make any sense, because you say that port 1 will act as output. Now you're writing move A comma P1. So essentially from P1 you are not supposed to get anything. You are supposed to send something to P1. So you are asking, what if I want to know what P1 contains, right? Something like that.
Yes, sir.
So for that, you need to go through the labs portion and you need to go through Appendix C2. This is related to hardware configuration as well. Normally, we do not cover this, but still, if you are interested, you can go through it by yourself. Is that okay? You are trying to know the port latch configuration, that what is the configuration at present. That is what we are trying to know. So for that thing, you need to go through some hardware connection as well, most probably. I don't know, because I myself have not ever gone through that port latch. I just know that is known as the port latch, but we have never gone in deep over there. But curiosity is good. If you really have the curiosity, I'll suggest you that, go through it. Still, if you face problem, you can let me know. Then I will, of course, I need to study. I will study and I will get back to you. Okay? Okay, any other question?
Sir, can you explain the part C again?
Part C. Oh, part C. Okay. So send a low to high pulse on this pin. So what is the meaning of a low to high pulse? This is what your pulse look like, right? These are your pulses. So low to high means your pulse will contain low and then it will suddenly go up. This is known as your low to high pulse. So how can we send a low to high pulse? First of all, we'll send a 0 or we clear it. That means it becomes 0. Then we set it to high. That means we make it 1. So that is what makes it a low to high pulse.
Sir,
this one simply indicates that the data has been read. That's it, nothing else.
Sir, reset value স্যার সবগুলোর জন্য 1 না, মানে ক্লিয়ার ভ্যালু দিলে তো
রিসেট ভ্যালু সবগুলোর জন্য 1।
স্যার তো মানে স্যার CLR যদি আমি কমান্ডটা ইউজ করি তাহলে তো স্যার এটার ভ্যালু মানে পিন ভ্যালু 1 হয়ে যাওয়ার কথা না?
Clear is not reset. Clear is CLR. Clear is clear. The instruction for reset is different. That is not your reset instruction. Okay.
Okay, sir.
I will highly suggest you that go through table 4.4 and 4.5. This contains nothing. The instructions that we learned so far, like set, bit, clear, complement, JNB, all these instructions actually are listed in table 4.4 and 4.5. You can understand it by yourself and also go through rest of the examples. All the examples are similar. Almost similar to this thing, and the examples are very easy to understand. With this, our chapter 4 comes to an end. This is probably the shortest chapter, and there is nothing complicated over here. Let me just take your attendance. After that, I will let you leave. To go to section D.